Hi, my name is Sean, and I'm presenting our work, Learning Task-Informed Abstractions, a representation learning approach for model-based reinforced learning in complex visual domains. This is a joint work with Gu Yang, Pulkit Agarwal, and Tommy Akola at MIT CSAIL. Model-based reinforcement learning has achieved impressive results in control with visual inputs. For example, the state-of-the-art Dreamer agent can master continuous control domains in the DMAN control suite, and long-horizon discrete control tasks such as Atari games with a sample complexity comparable or better than state-of-the-art model-free agents. Model-based agents first learn a world model from the visual observation, and then conduct policy learning inside the learned world model. To make sure that the learned latent state fully encodes information from the observation, a proper approach that is commonly used in state-of-the-art model-based agent is to learn to reconstruct the visual inputs using the pair of encoder-decoder networks. However, real-life control tasks are much more visually complex. Take this game, for example. Most of the features in this video are irrelevant to solving the task. Therefore, a full reconstruction of the image observation stretches the finite modeling capacity of the world model, making it challenging to capture those features relevant to solving the task. To see this, let's first consider a simple experiment, where we inject complex background videos to the DeepMind control task, cheetah run. We trained the reconstruction-based Dreamer agent on these two domains. In the figure on the right, we visualize the policy performance in the vertical axis, and vary the number of parameters in the world model along the horizontal axis by double, same, and half of the original implementation. Not surprisingly, the performance with the simple background is only marginally affected by model capacity, which shows that even the smallest model is sufficient for learning the features necessary for solving the task. Now, if you look at the domain with the complex background, the agent's performance is a lot worse. We also notice that the performance decreases monotonically with smaller models. This trend indicates that complex visual clutter stretches the modeling capacity of these model-based reinforcement learning agents. And the motivation of this work is to overcome this issue, to enable model-based reinforcement learning in complex visual domains. First, let's take a look at how we learn the world model. Our proposal, learning task-informed abstractions, explicitly models the task-relevant state and the task-irrelevant state in two separate streams, which we refer to as the task model and the destructor model, respectively. We incentivize the task model to capture task-relevant information by forcing it to predict the reward accurately. On the other hand, we discourage the destructor model from capturing task-relevant information by constraining it not to predict reward using an adversarial loss. By having the two models jointly reconstruct the input observation, the task model can focus on capturing task-relevant information, while the destructor model is biased towards capturing destructive information. Now we have learned a model of the world, let's take a look at how we learn policy. During policy learning, only the task model is used to generate the imagined routes. We sample imagined routes from the learned task model and train the policy through an actor-critic algorithm over the imagined routes. Note that the destructor model is never used for model-based routes. To recap, our method, learning task-informed abstractions, disentangles the world model into two separate streams, a task-relevant stream and a destructor stream. To prevent the degenerate solution where the destructor model captures no information, we introduce an extra last term, which refer the audience to our paper for more details. Lastly, the performance of our method is lower bounded by that of Dreamer. Our method extends Dreamer to challenge visual domains, and when the destructor model captures no information, our method reduces to the Dreamer agent. Qualitatively, we show the raw observation in three different domains on the top line, and inspect the decoded images from Dreamer versus from our method. Dreamer, which learns the single word model, does not distinguish between task-relevant information and task-relevant destructions. The image reconstruction shows that Dreamer's word model fails to capture the position of the agent accurately. On the other hand, our method, task-informed abstractions, accurately capture the position of the agent. This is because this destruction information is taken care of by the destructor model, which enables the task model to focus on those information that's relevant to the task. Our method outperforms baseline methods in most DeepMind control suite tasks, including strong bisimulation-based model-free baseline DBC. Atari games naturally contains visually destructive features. Our method also improves Dreamer's performance in several Atari games. In Demon Attack and Yard's Revenge, our method outperforms strong model-free base like DQN and Rainbow trained for 200 million steps, when our method is only trained for 100 million steps. In conclusion, our method, task-informed abstractions, enables model-based RL agent to learn efficiently in visually cluttered domains by adversarially learning disentangled world models. The paper, code, and video can be found at the project website, shelfie.co/TIA.